Today's discussion with the proof of theorem 10.1. We have already seen the statement, but let's see it once more. So it says that if we have a non-empty finite set which already is ordered, there is an ordered relation on the set, then it has the same order type as this finite set, which is a section of the set of positive integers. So you know how this is ordered, that is, it gets its order from the original set of positive integers, and that is why the non-empty finite set is well ordered, because this one is well ordered. So let's now prove this. But before we start the proof though, let me just introduce a notation that will make our life easy. It's not given in this text. I didn't find it anywhere, I don't know why. Note for a finite set S, let this denote its cardinality, that is the number of elements. Cardinality. Okay, let's now start the proof. Let us first give our set some name. Let A be a non-empty finite set that is ordered by some ordering relation. We just need to know that A is an ordered set. We do not even have to write any symbol for the order in this proof. Okay. Now the first thing, well, of course, this is what we have to prove, that A has the same order type as this section. But we first claim something else. We claim that A then has a maximum element, a largest element. We claim that A has a largest element, and we are going to prove this claim by induction. Induction on what? Induction on the cardinality of A, the number of elements in A. The claim is trivially true if A has only one element. See, instead of having to write if A has only one element, we can just simply write this. That is why I needed this notation. If A has only one element, obviously that itself is the largest element. So our claim is true in this simple case. Let the claim be true for all non-empty finite ordered sets with cardinality n minus 1, where n is at least 2. So that means this is our induction hypothesis. Let our set A have cardinality n. Alright. Oh, by the way, why do we need n to be at least 2? That is because we are stating the induction hypothesis for non-empty finite sets. So with the least possibility when n is 2, still in that case n minus 1 is 1. That is, there is something. Okay, that is why we need this restriction on n. Alright. So A having n elements of course is non-empty. So we can arbitrarily choose an element in A. Choose any element, say A0 in A. Then removing A0 from A, we get a subset of A, which is also a non-empty subset. See, the non-emptiness of this depends on the fact that A has n elements and n is at least 2. So even in that smallest case where A has 2 elements, if you remove A0, there is still 1 element left. So this is non-empty. Also, this is a subset of A, so it is finite as well because A is finite. Additionally, it is also an ordered set because it's a subset of A and A is an ordered set. So that's why we write these things. Is A non-empty finite ordered set such that its cardinality is n minus 1. So, by the induction hypothesis, A difference A naught has a largest element. Let's call it A1. Now it becomes clear that the largest element of A is either A0 or A1. Okay. The little argument that you have to go through mentally to see why that is the case is so easy that I am not going to go into that. I am leaving that to you. The largest in this set is A1. So if you include A0, it may be larger than A1. In that case, that will be the largest. I have already said this to you right now. Or A1 itself is the largest. Clearly, the larger of this end is the largest element of A. Okay. So, the claim follows by induction. We have thus proved that every set of the type we are considering has the largest element. Now we prove our main thing, and that too we are going to do by induction. Next, we claim that there exists an order preserving bijection between A and this for some positive integer n. Actually, although we are saying here for some, but we know what this n is. This n has to be the cardinality of A. The claim is trivially true if A has only one element. Why? Because in that case A is a singleton set, and so is this section of positive integers. I mean, in that case we will take n equal to 1. So we will have the singleton set having only the integer 1, and the trivial function which maps the single element of A onto 1, integer 1 obviously is a bijection, and it's also an order preserving map, and that proves that that singleton A has the same order type as that section of positive integers which has only the integer 1. So anyway, that case is trivially true. Let be true for all non-empty finite sets. I should not write just finite sets. Non-empty ordered sets or non-empty finite ordered sets. Of cardinality n minus 1, same as before, where n is at least 2. Let A have n elements, that is, let A have cardinality n. Let B be the largest element of A, which now we know exists because we proved that in the first half of our proof. We are now going to use this B. Now, so in that half we removed A0. Now we are removing B from A. The largest element of A is a non-empty finite ordered set. So, by the induction hypothesis, there exists an order preserving bijection Well, I am not again writing here that this set has cardinality n minus 1 because we did that anyway. I am actually writing a lot. You need not write everything at this level, it's not necessary. You can skip some things, But to make the presentation more clear, I am just writing everything. So there exists an order preserving bijection f, let's call it f prime, from this set into this section of positive integers. Now define another function f from the entire set A into this section of positive integers by the following rule. F of x is defined to be, I am using a colon before the equal sign. This I am adopting from Terence-Tau's analysis. This means that something is being defined. The side on which you have colon is the thing that is being defined, and the meaning lies on the other side of the equality. So f of x is defined to be equal to f prime of x if x belongs to a difference b, and it is equal to n if x is equal to b. Okay, so this is a function. Function, it's a bijection and it is order preserving. And in showing this, the similar facts about f prime will help you. F prime is a bijection, f prime of course is well defined, and f prime is order preserving. Let me just go through the steps briefly. I won't really do it systematically here. This part is going to be left to you. So what will you do first of all if you want to show that f is well defined? Well, you just take an input from the domain of, suggested domain of f, and see if you get a unique output in this second set. So that input may either lie in the set A difference B, or that input may be equal to B. Let us see this isolated case first. Say your input is B, then the output is N, which is a unique element in this set. Okay, so this part of the function is okay. It really is giving you an unambiguous output for a given input, and that output lies here. But if your input is coming from here, then the output by this definition is the output if you apply the function f prime to that input, which makes sense because this A difference B is actually the domain of f prime. Because f prime is well defined, this f prime of x is a unique output here. So obviously that is also a unique output here, and that is why f is well defined. Next, you have the job of showing that f is a bijection, and then that f is order preserving. Okay. So if you come to the issue of showing that f is bijection, how do you show that f is one-to-one, say? You can show it in two different ways, although they are equivalent. Either you can take two distinct inputs and show that their f images are also distinct. This is one way. Or you can take two inputs for which the images are equal and then show that the inputs are equal. Any one of these two ways you can choose. Say if you choose this way, then what? Say you have chosen x1 and x2, for which you don't really know yet whether that happens or not, but for which this happens. Then you have to divide that part into some cases. What will happen if x1 and x2 are both equal to b? That is one case. In this case, on this side you have n, on that side also you have n. But in this case there is actually nothing to do at all, because your aim was to show that x1 is equal to x2 and that you are getting anyway. There is another case. Say x1 is b, but x2 is not b, means it's in this set. Okay, so wait, what did I write? It's in this set, not outside the set. Then by the definition of the function f of x1 is n. However, f of x2 is what? F prime of x2 by definition. Now, is it possible for this f of x1 to be equal to this f of x2? No. Why? Because you see, f prime is a function which maps, the outputs lie here, and n is not one of the outputs. That is why you cannot possibly have this equality if this is the case. That means this case actually does not arise if we are having this. So this case itself is ruled out. Similarly, there is a third one. If x2 is b and x1 lies here, then also you get a similar problem. So that case also does not arise. There is, however, a fourth case. The fourth case is this. x1 and x2 both lie here. Then, by definition, this equality reduces to this. F prime of x1 equals f prime of x2. However, you already know that f prime itself is a bijection, and so it is injective, it's one to one. That is why from this equality you further get x1 equal to x2. So you see that the cases 1 and 4 actually do give you x1 equal to x2, and the other two cases are in fact non-cases. So in any case, if this is the equation you start with, then you end up with x1 equal to x2. That is why your f is injective. Similarly, you have to show that f is surjective and it is order preserving. I am not going to do that. Okay. So once you do that, then your thing is over. Let's see how it is over. Then f is an order preserving bijection. Okay, so that part you have to show. So the second claim follows by induction. And that's it. That was our main objective. So this completes the proof. What does this proof, what does this result mean? It means that if you have a finite non-empty ordered set A, then there exists a bijection of A with some section of the positive integers which is also order preserving, and that is why A has the same order type as this. In fact, The n here is nothing but the number of elements in A. As such, it can have only one order type, namely the order type that this ordered set has. And that is why, because this is well ordered, A is also well ordered. So for finite sets, you can have only one order type. However, this situation changes drastically when we go from finite to infinite sets. Let's take these examples. You consider these sets of positive integers times z plus times z plus, and this. These are all infinite sets and all of them are well ordered. In fact, z plus is already well ordered, we know. The others are Cartesian products of well ordered sets, which are also well ordered in the dictionary order that we proved in the previous video. However, in spite of all of them being infinite and well ordered, they have all different order types. To see how, you can proceed like this. A1 be the set of those elements x in z plus such that x has no immediate predecessor. Okay. Similarly, we define A2 in the second set and A3 in the third set. Then one can check that A1 has only one element, A2 has n elements, and A3 is infinite. So obviously, these first three sets have different order types, because in them that similar set A's, the A's have different numbers of elements. To see how these sets are still different from the fourth one, we can next consider this. In each of the sets, each of the sets means in each of these sets, let Bx be the set of elements with no immediate predecessor and which are less than x. So you understand what Bx is. Say you consider the set of positive integers. There you choose any positive integer, that is your x. Then Bx will be the set of those positive integers which do not have immediate predecessors and at the same time which are less than x. And the similar Bx's are there in the other three sets as well. Then, for the first three sets Bx is finite for every x. Okay, I mean in each one of the first three sets, if you consider Bx for any element x in that set, it will be finite. But for the fourth one, that is this one, Bx is infinite for some elements x. Exactly why these statements are true, I am leaving those parts to you. Okay, but this is how you can show that they are of different order types. So obviously these sets will now all be of different order types than this one, because here we have infinite bx's for some x, whereas that's not the case in the first three. Okay, so that's how we can have infinite ordered sets which are all well ordered. And oh, one more thing I forgot to say, they are all actually countably infinite. That fact is also there. So their cardinalities are same. In spite of that, they have different order types. That's not the case with finite sets. Once you have, say, a set with 100 elements, you can order it in any way you want. You have another set with 100 elements, you can order that set also in any way you want. Both of them will have the same order type as the section of integers which has the first 100 positive integers. Okay, so there is no other order type, only one order type for one positive integer. Alright, now the ordered sets that we have considered so far, the well ordered sets, all have been countable. Now the natural next question to ask is there any uncountable well ordered set? So if one tries that to this, you see, if no matter how many copies of the positive integers that we take and consider Cartesian product, in the dictionary order we are going to get well ordered sets only. So what happens if we take this, the Cartesian product of infinitely many copies of Z plus? Its elements become infinite sequences of positive integers. Now on this set, of course, you do not immediately have any extension of the dictionary order, you have to define it. You can define an order on this set following the definition of dictionary order like this. Say you have two sequences of positive integers, infinite sequences. We will call this sequence less than this sequence if there exists a positive integer n such that xi is equal to yi for each I less than xn is less than yn. One can then verify that this is a legitimate ordered relation on this infinite Cartesian product, which is like, you can call it a dictionary order, a kind of dictionary order on this. However, this is not and it's not a well ordered set with this order. The reason is this: let A be the set of all elements in this of the form this. So these are sequences of integers where nearly every term is 1 except one term, which is 2. Now this 2 can appear anywhere. It may be the first term of the sequence or second or anything. You can verify that as you slide this 2 towards right more and more, you keep on getting smaller and smaller elements. And all of them by definition lie in A. So A, in spite of being non-empty, has no smallest element. So that is why this set in this order is not well ordered. Fine. So if this dictionary order fails to make it well ordered, is there any other order in which, with respect to which this will become well ordered? And the answer surprisingly is yes. And it is one theorem. So that theorem itself is called the well ordering theorem. So this theorem, its name is the well ordering theorem. What it says is that, say you have any set A, then there exists some ordered relation on A which is a well ordering, which will make the set A into a well ordered set. Or to put this more simply, every set can be made a well ordered set with some ordering relation. This theorem was proved by Zermelo in 1904. Zermelo of your Zermelo-Frankel choice set theory. And it really astonished the mathematical world because it is so general, but there was considerable controversy and debate regarding its correctness. So the thing here is that it is an existence theorem. An existence theorem, you know very well, is a theorem which says that something exists. And or maybe I should say the proof is an existence proof. It tells us that something exists but doesn't really give us any concrete way of how to construct that thing. Okay, it's a logical proof. So mathematicians very carefully went through the proof in hope that they will be able to spot some mistake. So no mistake was found. Instead, it was found that the only place where there may be some doubt is an application of the axiom of choice. The axiom of choice essentially just tells you this, that say you have a collection of non-empty sets. In each set there are some objects, some elements. There may be infinitely many such sets or finite something, at least one set is there, but all the sets are non-empty. Then the axiom says that you can choose one element from each set. The way I have drawn this diagram, it may give you the impression that these sets have to be disjoint. That's not the case. They may have overlaps, but you can choose one element from each set. It's a very simple and plausible axiom which should be true. However, this leads to things like this. That is why many mathematicians initially did not want to accept this axiom as a legitimate axiom. They thought that no, I mean it's just so general that something is wrong with this. Nowadays, however, mathematicians don't really have that type of feeling. They accept the axiom of choice as a legitimate choice in set theory. Okay, and we keep using it every now and then whenever we have to make an arbitrary choice from actually infinitely many sets. Because if you have finitely many non-empty sets, there somehow you can manage without using the axiom of choice. Mainly it is applied when there are infinitely many arbitrary choices are involved. Okay. So anyway, this gives rise to the well-ordering theorem. So I will have to end the video here itself because it's become really long. In the next topology video, we will use this well-ordering theorem. We are not going to see any proof of this. Okay. The proof, the author says, is of more logical interest than mathematical interest, that how it logically follows as a consequence of the axiom of choice. So it's interesting to logicians, not exactly to mathematicians. We are going to just simply accept this as true, and we will see its consequences. Finally, using this, we will show that there exists a minimal uncountable well-ordered set. That's what we want. Okay, so let me end the video here itself. And tomorrow, of course, we have our uploads, and tomorrow we have +1 and +2 mathematics. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical World. Have a nice day.